Assalamu alaikum students and welcome to another lecture of Slate. This is Khawaja Yasin and let's study chemistry under Slate. So students, in the last videos, you must have seen the other videos regarding moles. I told you and we all know that how important the concept of moles is for the students of both O and A levels. So now in today's lecture, we are going to talk about two very important concepts, percentage purity and percentage moles, percentage yield. In this video, we will just be talking about the basic concepts and we'll just be solving a few basic questions for both percentage purity and percentage yield. In the next videos, we will be solving A levels questions for the same concepts because they are obviously more difficult than what we experience in O levels. But initially, we need to understand the basics of both the concepts. So first, let's talk about percentage purity. So students, whenever we talk about something, whenever you buy something from the market, it does matter how much pure it is, how much the pure substance is present in that thing. For instance, you're getting a stone out of somewhere. For example, which stone? For instance, limestone. And let's assume this is a rock of limestone. And limestone is calcium carbonate, as we all know. So let's assume that you have gathered that from a mountainous area or somewhere. And obviously there will be impurities present. For instance, these are the impurities. Let's assume this is a 5 kg stone, that's a huge stone. And we have 1 kilogram of sand inside it, the pink one. Let's assume that. So what will we say about its purity? How much pure is that stone? So for that, what do? We normally just take the mass of pure substance, which is if 1 kg is the impurity, so the pure would be 4 kg, and we divide it by the mass of the impure substance. Impure means having both pure and impure substance together. So 5 kg divided by 4 kg into 100. And we call it O. That's 80% pure. So that's what the concept of purity is. Now, the very similar calculations with the very similar formula applies in the concept of moles. For instance, it's a very simple formula. We will be talking about the tips and tricks regarding this formula. So whenever you have to talk about percentage purity, that is mass of pure substance divided by mass of impure substance. And I repeat, because that's a common confusion among students, that when we talk about impure, we talk about both pure substance plus the impurity. So you will not just consider impurity all differently. Impurity is a part of the impure substance along with the pure one. And you multiply the value with 100 because it's a percentage. So one important tip regarding this formula, always know that this needs to be a smaller value. Because students sometimes get confused during the exam. They get two different values and they just get confused which value to use during the whole calculation. And the lower value is a larger value. Because if your numerator is higher than denominator, for example, this becomes a bigger value. In the previous example, let's say we do 5 divided by 4 into 100. That would give us a 125% pure result, which is completely impossible and absurd. So remember, always the value in the numerator is the smaller one and the denominator is the larger value. Because as I repeat, it's a common confusion. So now let's talk about a question. This is just one formula and we just have to apply this formula. We just have to calculate the value. Now, 5 grams of impure sulfuric acid is dissolved in 1 decimeter cube of water. 25 centimeter cube of the solution required 23.5 centimeter cube of 0.1 mole per dm cube NaOH to complete the titration. So as you can see, the mass of impure is already given to us. 5 gram was impure. So we will just have to calculate the value of the pure substance. Let's see what we have to do. So in case, calculate the percentage purity of the acid. Since we are finding something regarding the acid is the unknown value. And that makes NaOH our standard, which is the known value. So remember in the previous lectures, we talked about the first step is either to make the equation. So let's make the equation. H2SO4 into plus NaOH will give us Na2SO4 plus water. That's neutralization. So we take 2 moles of NaOH and 2 moles of water. That's the chemical equation. Now we find out the moles of the standard. NaOH is the standard. So let's calculate the moles for sodium hydroxide. And obviously we have the volume, we have the concentration. So N equals to C into V and divided by 1000 as the volume is in centimeter cube. So concentration is 0.1 and the volume is 23.5 divided by 1000. And that makes it a value of 0.00235 moles. The unit is very important, as I repeat. So students, we found the moles of NaOH. Now what can we do? We can find the moles of the unknown. And the step is the molar ratio between the known and the unknown. So we draft a molar ratio between H2SO4 and NaOH. Initially, we write the moles from the equation. So H2SO4 has just 1 mole. So 1:2. And now we have the moles for sodium hydroxide, 0.00235. That's X. We just cross multiply the values if you remember that. So what happens? X equals to 0.00235 divided by 2. So let's calculate the value, what the answer comes. The answer is 0.001175 and we call it moles of H2SO4. You can also write that in scientific notation. That would become 1.175 into 10 raised to power minus 3 moles. Students, now we have calculated the moles. What do we do next? From this value of moles, we need to see what we have to do. We have the volume of this solution, which is the impure solution of acid. Now let's understand the concept. Initially, I just did the normal calculation because obviously that was very basic for you to do. But what's happening in this reaction? We have made a 5 gram per dm cube solution of sulfuric acid. So this is a 5 gram per dm cube solution of sulfuric acid. Obviously, it's impure. When I'm going to react this sulfuric acid with NaOH, when I'm going to neutralize this. So students, since it's an impure one, only the pure sulfuric acid reacts. Whatever value of the moles I'm getting, that's the mole value of the pure material present inside the impure solution. So only the pure H2SO4 reacts. That's an assumption from our end, but that's how we're going to do the calculation. So from this, only the pure material reacts. Okay. So we know that here we talk about the pure moles. And since we have the impure value, as per this formula, we have to find the pure one. And we have the impure value not just in grams. This is gram per dm cube. It's like a concentration. So students, we need to find the concentration of pure in gram per dm cube, because this is not just gram, this is gram in a dm cube. So in the previous video, we also talked about this concept where we how to calculate the gram per dm cube value from mole per dm cube. So we just have moles here. So what is mole per dm cube? Mole per dm cube is concentration. So we have to find the concentration of a cell. So how to calculate the concentration? Simply, we use the formula of N equals to C into V. Do we have the volume? We definitely have the volume. So moles, we just calculated them here. So 0.001175 into C into, that was, let me see again, sorry, 25 divided by 1000. We get the value where C equals to 0.001175 into 1000 divided by 25. So let's see what the answer comes in. So the answer is 0.047 mole per dm cube. In the last video, we talked about that let's assume that we're going to assume that our solution is, it's obviously in 1 decimeter cube of solution. The mass is, which was gram per dm cube. So the gram per dm cube is just 5 gram now. And we use this value of moles now, because this is mole in a dm cube. So in 1 dm cube, the moles are 0.047. So when we have the moles, when we have the mass, obviously this value was for impure. So how to calculate the mass of pure? We have the moles in a dm cube. We simply use the older formula. Mole equal to mass divided by mr. So here we're going to do, what we're going to do is 0.047 into mass divided by the mr of the H2SO4, the acid. So it's very basic, but still let's calculate it. H2SO4. So H2 is 2, sulfur is 32, and oxygen is 16 into 4. So this becomes 40 plus 64 plus 32 plus 2, and that becomes 98. So this divided by 98, so mass will be 98 into 0.047. Let's see what the answer comes in. The answer is 4.6 grams. So students, this mass is the mass of pure, but in 1 decimeter cube of solution. So we have the mass of pure in a dm cube solution. We had the mass of impure in a dm cube solution. We'll simply incorporate the value in the formula of percentage purity. So that would be 4.6 divided by 5 into 100. Let's see what the value comes in. Divided by 5. And that is simply 92%. So I repeat, this is the answer. Obviously, always the smaller value goes on top, because obviously in the exam you can get confused that one value you have calculated and the other value was given to you. So I would just repeat what we did here, because obviously this was a confusing question. The 5 gram was not just the mass, it was the gram in 1 decimeter cube. So just to compare this gram, this mass, we need the mass in dm cube. We could have simply calculated the moles from here using n equals to mass over mr, but these moles are the moles in 25 centimeter cube, not 1 decimeter cube. So we needed moles in a dm cube. So these were the moles in dm cube. And then we compare that with the mr value. We multiply it with the mr and we get 4.6 grams. And that is the mass in a dm cube. So that is how it's done. Now let's talk about the other concept. The other concept is of percentage yield. What is yield in the first place? Yield is the amount of product being formed. Students know that. And you all know, like it happens in our normal or daily life. You calculate something, you plan something, you execute something, but it never goes the way we want it to go. Because obviously there are different hurdles in between, there are different challenges, there are different issues. So the same goes in experiments, in labs. When we calculate something, we calculate through molar ratio, we calculate through values that give us our theoretical yield. Theoretical yield, or sometimes we call it calculated yield. Let me put that in bracket, that's not a division mark. But this is theoretical. But when we perform it experimentally, the result is always lesser than the theoretical yield. There can be various experimental errors, there can be various instrumental errors, there can be human errors. So know for sure that the actual or the experimental yield is always lesser than the theoretical yield. So we divide the experimental, or we can also call it actual yield, by the theoretical yield, and we multiply it by 100. So this is just one basic formula. And just like the percentage purity, the smaller value is in the numerator and the larger value is in the denominator. So that is what we know about the percentage yield. Know one thing, like in the 99% cases, since you're solving it on paper, you cannot calculate the experimental yield. So experimental yield is given. Sometimes it's not given. Why? Because in that case, they've already given you the percentage yield. So you can cross multiply and use the formula. But experimental or actual yield is given because that is something you cannot calculate, because that's experimental. So let's see a past paper question in this regard. This is again a question of hydrated salts. Okay. Crystals of sodium sulfate, 10 water, which is decahydrate, are prepared by titration. Perfect. 25 centimeter cube of sodium hydroxide having concentration of 2.24 mole per dm cube. That's the concentration. So first, that's not a question of moles, that's a question of the preparation of salts. 25 centimeter cube of aqueous sodium hydroxide is pipetted into a conical flask. We use pipette and put it in a conical flask. A few drops of indicator are added, and using a burette, dilute sulfuric acid is slowly added until the indicator changes color. The volume of the acid needed is to neutralize the alkali is noted. Perfect. Suggest how would you continue the experiment to obtain pure dry crystals of sodium sulfate decahydrate, 10 water. So, no, in order to obtain the pure crystals, we need to repeat the experiment because we have indicator added and the color change was there. So the colored crystal will not be a true crystal. So we need to repeat the experiment. The purpose of using indicator is to get the end point. We have gotten our end point. So we're going to repeat the experiment, but this time without the indicator. So we repeat the experiment. without indicator. And after that, add the noted value of acid from the first experiment. Obviously, that would neutralize our alkali. What's the next step? Since this is sodium sulfate is a soluble salt, what will be our next step? Students, our next step would be to dry the precipitate. How do we dry the precipitate? Evaporation until dryness, or simply crystallize the salt by putting and heating the solution in an evaporating dish. Obviously, we've got the crystals, but then we need to dry them. Dry the crystals before that, sorry, my apologies. Filter the solution and then dry the crystals using a filter paper or an oven. Dry the crystals using filter paper or towel or oven. So that's a question from the preparation of salt, a 4-mark question. That's a huge question. And that is why I could not skip anything, because in the marking scheme, for 4 marks, they will have 4 to 5 points or maybe 6 points that you have to write to get full marks. So that is why it's better to concise everything inside, because it's a 4-mark question. Now, as we talked about the percentage yield formula, actual yield over theoretical yield, let's see what the question is about. Using 25 centimeter cube of aqueous sodium hydroxide, 2.24 mole per dm cube of 3.86 grams crystals were obtained. So students, as I said, it's given. And they've told you that this was actually which was obtained. This was the actual value. So this is the actual yield. Calculate the percentage yield. Okay, steps are given. Let's see what's happening in the equation first. 2 moles of sodium hydroxide are reacting with a mole of H2SO4 to give 1 mole of Na2SO4 and 2 moles of water. But when this anhydrous salt of sodium sulfate is added with 10 moles of water, we get 1 mole of the crystal. Let's see what the question demands us. Number of moles of sodium hydroxide used. What are we going to do? 25 centimeter cube is the volume of sodium hydroxide. 2.24 mole is the concentration. So C into V, 25 divided by 1000 into 2.24 mole per dm cube. So let's use the calculator and let's see what the value comes in. That is 0.056 moles. Now, the maximum number of moles of sodium sulfate crystallized salt, which is decahydrate, that could be formed. So this is, let's look at the question, let's look at the equations. Obviously, we have calculated the moles of sodium hydroxide, but that's in a different equation. And the crystallized salt, the hydrated salt, is in a different equation. What will we do here? We need to make a relationship. We know that 2 moles of sodium hydroxide can give 1 mole of Na2SO4, sodium sulfate. And 1 mole of sodium sulfate makes 1 mole of the hydrated salt. So from that, we build a connection, we build a relationship that 2 moles of sodium hydroxide are needed to make 1 mole of the salt. So this is obviously 1:2. Let me erase it. So NaOH ratio Na2SO4 10H2O. 2 moles of sodium hydroxide, 1 mole of the salt. How many moles of sodium hydroxide do we have? 0.056 and X. We simply do the cross multiplication and the answer turns out to be Na2SO4 10H2O equals to 0.028 moles. We just divide this value by 2. So 0.028 moles. The mass of 1 mole of sodium sulfate decahydrate is 322 grams. So courteous of the examiner that they have already given you the mass. The maximum yield. What was the yield? Yield was the amount of the product. So how do we calculate the amount or the mass of the product? We have the mass. Sorry, we have the molar mass and we have the moles, which is 0.028. We simply use the formula N equals to mass over MR. So moles are 0.028. Mass is unknown to us. MR is 322. So let's calculate the value. Let's multiply 322 with 0.028. And that would be 9.02 grams. So students, this is the maximum yield of sodium sulfate. That is what you calculate on paper. But in actuality, how much did we get? We only got 3.86 grams. So let's use the formula. Actual yield, which is 3.86 grams, divided by theoretical yield, which is 9.02, and we multiply the value by 100, and the answer turns out to be, let's see what the answer is about. And the answer is 42.8%. And that's what we know about the percentage yield. So that's the two major important concepts, percentage yield and percentage purity. Let's do one question from hydrated salts. This is a tricky one because let's see what's happening here. Solution Y contains 30 gram per dm cube of iron sulfate XH2O. Again, you don't have the value of X, which is the number of moles of water in this hydrated salt or crystal. In a titration, 25 centimeter cube of Y, which is a solution of iron sulfate, reacted with 27 centimeter cube of 0.02 mole per dm cube KMnO4. This is a redox titration. Whenever we use an oxidizing agent like KMnO4, that's a redox titration. The equation for redox titration for O-level students, it's very tough. So that equation is always given to you. But we don't have the equation in this question. Let's see why. In the reaction, 5 moles of iron sulfate, H2O, react with 1 mole of KMnO4. Calculate the concentration of Y in mole per dm cube and the value of X. So let's see what's happening here. We do not have the equation. It's very difficult to calculate the equation here because we do not know the value of X. So obviously, with an unknown value of water, we cannot balance the equation. So what do we do here? In this part of the equation, they have already told you what you need for the molar ratio. That 5 moles of iron sulfate reacts with 1 mole of KMnO4. And that is all you need to make a molar ratio. So molar ratio can be done, but let's calculate the moles of the standard. Which is the standard? We know the volume, we know the concentration of KMnO4. So let's find the moles of KMnO4. So C into V. So concentration 0.02 and volume is 27 divided by 1000. Let's calculate the value. 0.02 into, and the answer turns out to be 0.00054 moles, or we can write it down as 5.4 into 10 raised to the minus 4 mole. That's the moles of KMnO4. Let's make a molar ratio here. Molar ratio between the salt, which is FeSO4 XH2O, ratio potassium manganate KMnO4. So for this line tells us that 5 moles of the salt reacts with 1 mole of KMnO4. We have the moles of KMnO4 from here. So 0.00054. We do the cross multiplication and we just multiply this value with 5. And that would be 0.0027 moles of iron sulfate XH2O. So students, we have the value of the moles of iron sulfate. What do we have to do next? Calculate the concentration of Y in mole per dm cube. How do we calculate the concentration from here? Just the simple formula, N equals to C into V. This N is of iron sulfate XH2O. We don't have the concentration, we just have the moles, which is 0.0027. Concentration is unknown to us. Volume, it's given. So 25 divided by 1000. So let's do the cross multiplication again. C equals to 0.108 mole per dm cube. We're done with one concentration. Now, how to calculate the value of X? Here we have this salt, 30 gram per dm cube of the salt. Now, what do we not know about the salt? We don't know the value of X. So X will be a number which will be multiplied with the mass. So what's the next step? We need to calculate the MR of the salt using this value. How will we calculate the molecular mass? We have the mole per dm cube concentration. We have the gram per dm cube concentration. And let's use the formula we have been using in so many questions. Or we can assume, or we can see that in a 1 dm cube solution, mass is 30 gram and moles are 0.108. So we just use the mass, moles equals to mass over MR formula. Let's calculate the value that we get here. So we know here that the moles are 0.108, the mass is 30, and the MR is unknown. So MR equals to 30 divided by 0.108. So this turns out to be 278. So what do we know from here? That the MR of this salt is 278. Our next step would be, wait a second, using this MR value against the salt. This is iron sulfate XH2O equals to 278. We know the MR value. So we know that the MR of iron is 56, that of sulfur is 32, oxygen is 16 into 4, dot water altogether is 18. So 278. So this is 56 plus 32. Let's add it here. That would make it 88 plus 16 into 4 makes it 40 plus 64 plus X18. So 88 plus 64, that would make it 140, 150. Let me calculate it. Let's not make any error here. So 88 plus 64, that is 152 plus X18 equals 278. So we're going to subtract this value, which is 152 from 278. And this turns out to be 126. So X18 equals to 126. So X equals to 126 divided by 18. And the answer is 7. So the value of X is 7. The salt is iron sulfate 7H2O. That means heptahydrate. So students, I know this was a very long and crazy video because that's what moles are all about. Different topics, difficult topics. And in the next video, we will talk about the most confusing topic of moles, which is limiting an excess reagent. So thank you so much for bearing with me. Allah Hafiz.